today's topic is going to be on refraction. This is continuing on from our last topic on reflection. Can anyone tell me what's being observed in this photo here? A post. Very good. How many posts do you see?
One, two, well, technically one.
One real one, and how many not real ones? So, this is a virtual image, and that is because of both reflection and refraction. So, just brainstorm here. What are some ways that we see refraction every day?
Straws in our drinks.
Okay, yeah, I see where you're going with that.
I don't know, it's a good example.
So we're talking about the bending of a straw.
Mm-hmm.
Okay. Anything else? How about magnifying glass? Is that an example of refraction? Yes, it is. Those are just two examples as we work our way into this topic. Give you a more clear idea of what we're going over. By the end of today's lesson, hopefully you will be able to describe and demonstrate your understanding in terms like reflection and refraction and transmission through different materials. You will be able to investigate refraction specifically. We are going to look at measuring refraction and see whether or not we can predict it. So, refraction is the bending of light as it travels from one material to the next. Now, the direction and speed of light changes based on the material it passes. So if light is always traveling through the same space, say it's all traveling in a single pane of glass, do you think light's going to change speed? How about if it's going from air into water? Probably. Now light travels at the same speed regardless in a vacuum, because there is no matter for light to encounter. Anybody know what the speed of light is? Yes, 3 million meters per second. Thanks, Heather. So C, which is our speed of light, equal to 3.0 times 10 to the 8 meters per second. Refraction works because light has to slow down when it encounters different material. I'm going to do a short demonstration, but I need one volunteer. It's very simple. It will only involve you walking. I promise. Sure, Heather. Okay. What I would like you to do is, starting at that end by the classroom door, walk towards me. Perfect. All right, now head back to the classroom door. And you have to walk in a straight line. If you encounter an object, you can just minimally go around it. All right, go. And stop. Thank you very much. Go ahead and take a seat, Heather. Thank you. Anybody know why I did that? Yeah, show how light travels. In a vacuum, would there be matter blocking light's path? What did I use as matter in this example?
Chairs.
Chairs and a garbage can. So, in the absence of matter, light can just travel in a straight path and it's unimpeded. When you have different matter represented by our objects, did it take Heather a longer time to get to me?
Yes.
Same thing happens in real life when light's traveling. even through air, even through water, it interacts with the matter that's present and it impedes its path. And that's what makes refraction work. Now, a few things we want to point out here. So, for our terminology, we have a normal line. Anybody know what normal line is? Recall, it is the line that is 90 degrees to a surface. What's another word for it? Perpendicular. So we got angle of incidence coming in. It hits or interface between two different materials. And the output one is our refractive ray. Remember that we always measure the angle from the normal line. Right there. So this would be, back to redraw it here. That's not very refractive, is it? That's more refractive though. And refractive ray. So this is the basic terminology that we're working with. We have our incident ray and our refracted ray. And these two different materials represented by an N value. Now don't worry about the N right now. We're going to get into it later. But for right now, just know that this is for our material 1. It has one N value. This is for material 2. It has a different N value. All right. So we have just one example of reinforced refraction, right? So we got our grade 8 science student, and he's trying to spear hunt a fish. Can anyone explain what's going on in this picture here?
It looks like the fish is in a place that it's not.
Yeah, so apparently, based on where he's looking, because remember that light travels towards our eye, so this would be some reflective beam, and this light is coming up, and if it wasn't refracted, right, we would see it right here, pretending a person was there. That's a refracted ray. I mean, it has to go towards our eye so we can see it. So this beam is traveling up and back to our eye. What we see is a virtual image because we just see this ray of light coming back towards our eye. So if we trace back this ray of light to where we see it, this is where the fish appears to be. Based on this image, if we aimed right here, would we hit the fish?
No.
No. So if we were fishing, where would we want to aim if we saw a fish here in the water? Front of it. Awesome. All right. Now this is just going over some different technologies where we see refraction. How do we see refraction in the environment? Would this be one example? Mm-hmm. Yep. So the apparent image of things in water. Ever noticed a road looking wet when you're driving? You guys don't drive yet. When you're driving with your mom and dad,
Yes.
like wet and wavy, that's refracted light coming from the sun, refracted heat coming off the road. How about a different technology? Can anyone guess one? And hopefully we can, because I wrote one on the board for you. Magnifying glass. Good work. Telescope would be another example. And anyone with glasses. When your vision's impaired, to some extent, it could be the light isn't landing on the same part that's supposed to on receptors of our eyes. So a pair of glasses is refocusing that light coming in so you can see. So anyone wearing glasses? Yes, that's a piece of technology, and yes, it's refracting light. Yes, question?
No.
Ah, awesome. All right, now for this one, either a notebook or a piece of paper, or just predicting in your head if you so choose for this exercise, answer the two questions. Can the pathway of light be predicted? And if so, how can we tell which way the light will bend? The second one will be more of a guess. First one is just a yes or no. I'm just going to give you guys a second to discuss that among yourselves and see what you have to think. No way?
Can't be done.
Can't be done? Okay. How about over here?
I think it can be done
You got an idea why?
because you can predict if an object that the light is hitting, if it will reflect, absorb, or one of the other words, the light. So then
Correct.
from that, you can predict which way the light will go.
All right, so we got a pretty good prediction here. There will be no fighting in this class, just to be clear. All right, so yes, you can. And yay, the law of refraction. So, I want you to pretend that in these gaps where I forgot to fill it in, is this theta 1 and this theta 2. So, for today, we won't require calculators, but here's the take-home message. N is actually a refractive index. It is based on material properties. So, if N1 is greater than N2, light will bend away from the normal. If the first medium, N1, is less than N2, it will bend towards the normal. N1 is equal to N2, there's going to be no refraction because it's the same material and you just realign through it. Now, one more thing to look at here. As I explained, refractive index is actually a comparison of the speed of light, which is always the same in a vacuum. That's represented by c, over its speed, which for the purposes of this is going to be v. So, if you had to guess, what does an n value of 2 mean? So, in a vacuum, light travels at its absolute fastest speed, and everything else is slower compared to it. So is this number going to be bigger or smaller than the bottom number? Knowing that this value is the absolute biggest it can ever be. Bigger. Gotta go bigger. This one's going to be smaller. So what we can really think of n value is how many times faster light is moving compared to the speed of light in a vacuum. So if this n value applied to, let's say, a piece of glass, light in the vacuum moves twice as fast as it does in that piece of glass. So that's what a refractive index means. Is that clear to everyone? If I had an n value of 3, how many times faster does light travel in a vacuum than through that object? 3 times. All right, here's the fun part. Now for this one, I'm going to ask you, please pull out your worksheet. I have your worksheet. All is one of our few simulations. If I had all the material set up in a lab, we could do this in person, but I found this one would be good enough. So, we're going to start with an example. Now, for this simulation, it says error is 1. Error is almost 1. What it really should say is vacuum, because that's absence of space. Matter, rather. So do remember that. Now, we have a refractive index for our first material of 1, and for our second material, 1.5. And I'm asking you to predict, will it bend towards or away from the normal? Talk about it just for a sec. Think about it in your head. What will it do? All right. Is anyone willing to share their answer? That's all right.
Should bend away from the normal?
Bend away. Let's see what happens. So, confirm this. Instant ray was what? Someone read it to me. 45. And our refractive ray was what?
28.1.
Towards or away? Towards. This is a case where N1 less than N2 goes towards. Just as stated earlier. Towards. Now we're going to change it a little bit and shut off our laser. Water to air. Yeah, it's crazy.
What?
Now, if our laser pointer was underwater, and it's now entering air, is it going to bend towards or away from the normal? Away. So our laser prediction. Now, ideally, I'd have you recording this down with me, because I've been so nice as to draw this out. So that was really what our classroom would be doing at this time. Let's see what happens. Away from normal. So, we got a refractive index, 1.33. Thank you. Another one. Angle of incidence was 45, and angle of refraction is 70.4. N1 was greater than N2. Away. Perfect. Now, what I would have you do in groups is going through, now that we've predicted them to observe, we want you to try to provide an explanation for this. So that's what you would be doing 5, 6, and 7. And since we have some time in class, I'd give you time to do it now. That would take about 5-ish minutes. So I was saying that we went through that, and you were able to come up with some predictions. We go over what we noticed. So, completing today's thing, we have that we can predict where refracted light goes, and that can be predicted by Snell's law. Now, we won't have to be worried about using this relationship right now. We're going to get into actually calculating it ourselves in later lesson. Refraction changes based on the material properties encountered, and this is based on and demonstrated by the refractive index. refraction is used in a number of optical technologies as we went through, and it can be seen in our everyday lives. Now, since you guys were so good going through this all, we are going to watch a video. All right. Let's get YouTube ads. Okay. I have a magnifying glass and a black marker. Black does what to light in terms of transmission, absorption, and reflection?
Absorb.
Absorbs. That's what's important here. So we have a black marker and a magnifying glass. What do you think is going to happen?
Absorb.
Okay, it's going to absorb it. Go outside. And it is absorbing the light. And the light is being focused on a point because it's being refracted by the magnifying glass. And after a little time lapse, it catches fire.
Oh my god.
And if it was a sunny day and this wasn't a winter term course, we'd be doing that today. Now we got a balloon. What could be happening here? What do you think is going to happen to the balloon?
It's gonna blow up.
Why?
Because
We're going to use the magnifying glass to do what to light / heat energy? Focus
refract
it.
it.
Yeah, focus it, and that's refraction. Good, not wrong. And it's going to. Let's find out. Wow. This one's really cool. 2 balloons. So he plates both. Size above. Which balloon's going to pop first?
What happened to the two? Are you different on that?
The 2 balloons are set up like
Oh, one inside.
one inside the other.
The
Which
one
one's going to pop
inside's
first?
gonna blow up
One inside.
first.
Why?
Because it's being absorbed and heating from the inside out.
Let's see what happens. One inside blew up first. So, just as a little note of this, as we go into our lenses, this is a convex lens, sort of, so it causes light to go in toward the point. Magnifying glass is also a convex lens. We have 2 convex lenses. Is it getting more focused here or here?
There.
Inside. That's why. Now that's all the time we have for today. As I said, our next topic we will be getting into is lenses. So please be ready to go over that for tomorrow. Nothing else floats.
Yay!